Hello, everybody. Thanks for joining us in this session today. Um, I'm so glad to be back here in person, given all of recent history. I guess we're all reminded how precious this interaction is to be, in person and in talk, have discussions on, topics that we like, to have these kind of presentations, but also, after this, discussions. So I'm really glad, and I hope you all are having a great Cisco Live Amsterdam. So today's this session that we are going to, for now, is going to be deploying VPNs over segment router networks. We're going to talk about an SDN approach. You might have heard about transport SDN, the word coming up quite frequently in the industry. So we'll kind of dig deep into this to see what are the things that we are talking about, and we'll shift mainly to the provisioning and automation side of it very quickly. So just to set the stage, it's not going to be a deep dive on any VPN or segment routing technology, but it's more about how to manage, deploy, and operate such networks using an SDN approach. To be in contact with all of us, to have good discussions, we have a WebEx team room, and if you like, you can join there. It'll be monitored. I'm on it, and the plan is to have it up and running to have discussions till at least February 24th. And of course, you may be able to reach me in other ways as well. I hope you do join so we can get more direct feedback and have lively conversations there. I did post the updated PDF of the slides. It's in the app as well, but I did notice that they didn't push all the slides, the hidden slides that are extra content that I won't be presenting, but it's in there as a reference. I just posted on WebEx Teams. The slide, the updated one will be pushed out. It takes, I believe, an hour or so. It may be there by the time our session ends. So if you don't see the hidden slides, that's what is the reason for that. What we'll start is to go through a technology review, briefly recap some of the use cases that we are trying to automate. We'll look into some of the VPN and segment routing related technologies, more of as a review. Then we'll look into some of the automation considerations and where we are headed as an industry, what are the things that are being talked about and being adopted by the network operators as well as by vendors, right? So we'll we'll do a high-level pass-through of some of the things, and then we'll look at the Cisco's controller for transport SDN, which and I'll show you basically how we can do all of this using that. It's mostly demos and a little bit of explanation of what's happening behind the scenes. So let's get started, right? So when we talk about transport services, these are typically the service that you're delivering as a provider to your end customers. Maybe you're a large enterprise and you have different departments. They need their own private network. These are usually virtual private networks, either L2 or L3. There are different technologies out there. The most common one is your RFC 2547 based BGP L3 VPN. EVPN is very popular and going forward for L2 VPN, but there are also legacy VPWS and VPLS type of technologies. Internet access is in itself a transport service. It can run directly on global routing table or on a VRF if you want. Then if you are a provider that's also providing peering arrangements to and internet access to your enterprise's customers, then you may want to have a service there. You can actually turn up and have them connect at different points of interconnect, and have public peering, private peering, all of that also to be considered as a transport service, and we may want to automate that, right? Multicast transport in itself is a big thing, right? If you're a content provider, then that's your main business. Then you actually have a lot of investment for multicast transport. Even otherwise, even an enterprise, multicast is being used for different things. Then your end customers are running L3 VPN. Then you're looking at MVPNs for that as well, right? And then looking at traffic engineering, RSVT has been out for quite a while, right? It's been deployed pretty broadly, and now segment routing is being deployed. It's come to the stage where lots of deployments are happening, and then segment routing traffic engineering is the one of the big things that you get with segment routing, meaning not only it simplifies your network, but traffic engineering in a more broad deployments becomes possible. RSVP was complex, and you did it only where you need it because of some of the challenges. And then SRv6 is something that's getting a lot of traction. I'm sure you must have interested. If you're interested, you must have attended some of the other sessions where they're going deep into SRv6. It's a relatively new technology. It has a lot of network programmability concepts in it, with the programming instructions embedded in the IPv6 address itself. Because we have so many bits, we can actually use some of those bits to tell the end provider edge router PE to do what to do with the packet when you get it, right? So that's new. In this session, we'll be talking mostly about segment routing. A lot of the segment routing and segment routing T that I'm talking about applies to SRv6 also, but I will, in the interest of time, I cannot show both of them. I'll show mostly MPLS. But remember that SRv6 works, at least from the outside, exactly same, but inside there are some differences. So one other thing is that when you're deploying VPNs, and then with the traffic engineering being something that you could deploy to get very specific granular SLAs, not just using shortest path routing, then you have to figure out how to actually deploy your service and bind it to a particular path, right? With RSPT, this was always going to be difficult, because then you basically either have a full mesh between all your PEs, and then you get basically one lane, and if you want multiple lanes, you can use something like class-based, tunnel selection, or policy-based, or there were different tool sets. A lot of them required a lot more complex configurations. But with segment routing, there are a lot more capabilities, because we have something called a color. So basically, any SR policy is a combination of head end, tail end, and a color, and you can actually apply different SLA treatments or objectives to those, and then you can actually have between the two same routers many tunnels with each of them with different behaviors in terms of how packets are treated, right? In SR, we call them policies, because it's basically an intent of what the behavior should be for the packets, instead of tunnel, which is what RSP tunnels were called. For point-to-point services, it's actually a little bit easy, because we say anything that's coming from attachment circuit, instead of just getting encapsulated and going to the egress PE, and use the egress PE label that was normal non-TE behavior, you can actually say just use the tunnel to just transit the core, right? So the configuration on iOS XR is preferred path. So preferred path, and then you give the policy name with SR policy, or RSP tunnel name with tunnel. So that's a little bit easier. But with segment routing, we have this concept called on-demand next hop. I'm sorry, which is basically very convenient to use for multi-point, where you can actually create policies on demand when you actually get a prefix that needs the policy, right? So that's on-demand next hop. In briefly, it basically involves you that creating of an L3 VPN policy to put a BGP color community. So when a egress PE sends a route to the ingress PE, as a part of the VPN advertisement, VPN v4, VPN v6, or eVPN, you put a route policy to say, add this BGP color community. The ingress PE gets it. It looks at the color community and realizes it needs a SR policy to be instantiated at the time. There is a template that tells that for that color, what is the behavior, or what SLA should be adapted, what is the constraint, things like that. Looking at the template, it'll bring up a policy on demand, as well as in the forwarding table, it'll steer any traffic that is going to that VPN prefix into the tunnel. All of that happens automatically, and the only thing you need to put a priori in advance is the template for the color, right? You just deploy all your templates on all your PEs, and then for every VPN, you decide what treatment that customer or the end customer needs, and you put a policy to map those prefixes to those colors. And this is important, because when we look at how to provision it, this is a really convenient way of doing it. Now, path calculation, again, this is mostly a review if you're not familiar with segment routing, TE, or general TE, because a lot of these concepts are general for TE. Some of them I'll point out where there are some special benefits with segment routing. If you're not familiar, I would encourage you to attend some of the SRT deep dive sessions that are happening, segment routing sessions. But when you actually create a tunnel, you're actually trying to avoid the tyranny of the shortest path, as they call it, right? Because all traffic from all points A to Z will basically, in a normal routed network, follow the shortest path. Basically ISIS, OSPF does calculate, all traffic goes through it, right? The whole point with segment routing is to actually have some control over which path it goes, and then how do you express those paths in the head end, which is where the traffic is starting, right? So there are different options. So just to recap, you can do explicit. This is in RSVPT, we had something called explicit routed object. Basically, you say to the head end, you build a tunnel, and you go first from A to D, and then to G, and then to Z, right? And then between A to D, for example, the hops will be routed based on routing, but all traffic, the tunnel will be built using RSP signaling through those paths. In segment routing, also you can do the exact same thing. You can do explicit routing, but there are some disadvantages of nailing up such paths, mainly because if that node that you're saying is a hop, it dies, then your service goes down. Usually what you do is you have a list of what we call as candidate paths. If the first one dies, the head end will go to the next one, and if the next one dies, at some point you need to give a what we call as a fallback, which is if all the explicit paths, usually you don't do more than one or two because it just becomes too complex, then you basically use a routed path. Basically say, just let IGP, follow IGP for the last option. Where you would do this is when you have very specific needs. In a sunny day, this is exactly the path I want the traffic to go, path option 1, path option 2. In a disaster, just pick any path, my service should be up. I know that I won't get the latency or specific policy-based routing for that at that time, but disaster, so I just need to get my packet across, right? So that's where you do explicit. Dynamic is where you actually let some function, mostly it can be done either head end or external, right? To actually run an algorithm, we call it constrained shortest path forwarding, right? Basically, not only you do calculate the shortest path, but you calculate the shortest path in the context of the constraints, right? The constraints can be many of them, and we'll review those in a minute. The important thing there is who is doing the path calculation, right? Most routers, head end, that are basically the source of their tunnels, can do this. That is basically local path calculation. The one challenge is that you do need to know the full topology of across which you're doing path calculation. And this topology is actually learned in ISIS or OSPF domains. There are standards to add traffic engineering related information. Those are called T extensions to ISIS and OSPF, and that information is there on all the routers in a particular ISIS and OSPF, right? The traffic engineering database. So the head end has visibility to that topology that it is participating in the ISIS or OSPF, but it does not have the visibility to other OSPF or other ISIS domains. And in a large network, you can't deploy one ISIS L2 or one OSPF area. You deploy many of those, and then you have to figure out how to actually do, not only routing. You have all those, unified MPLS, and then segment routing with our PCE. This is where we need a centralized path control function or path computation function. So in this case, the head end actually, we call it delegates a path computation, right? It says, I need a tunnel policy or a tunnel to be brought up to a tail end, and the configuration of that tunnel says delegate it to a path compute element. It'll actually use the PSAP protocol to request. It'll send a PC request packet, as it's called. Again, this is standards-based, so most router vendors support it, so it can be done in a multi-vendor network. And then the path computation engine in the central place, it's just a software function. It has connection to all the ISIS and OSPF areas in your large network. It can do path calculation across all of them and return the path back to the head end, and then head end just installs it in a forwarding table. It's in SRT, it's all source routed, so it'll basically put the stack of labels and send the packet out. So that's a centralized model for dynamic path calculation. A lot of the functionality that we really want is basically using PC delegated dynamic path calculation, because that's where you get the bang for the buck. That's where you can do what we call as SGN paradigm, where you express an intent and the network figures out what's the best path to send your traffic for that. In terms of how do you create these paths, right? So that's where you are creating your SR policies or tunnels. How do you do that? I mean, the easiest way is to actually configure them on the head ends, the routers, either using netconf or CLI interfaces. And we call them PCC initiated, the path compute client initiated, because either the head end is doing it itself, in which case we call it local, as we saw earlier. But in most cases, we want to delegate the path computation to the centralized path computation engine. So the PCE, think of it as a server. We also call it PCE, but the head ends are then clients, right? The client is asking for a path from the engine. Engine sends it back after doing path calculation. The reason this is important is that there are both ways of doing it. You can do policies, creation of traffic engineered paths through PCE. The technology allows that. So you go to PCE and you configure from router A to router Z. You want a path. The PC will not only calculate the path, but it will also program the head end to send traffic via a label stack, for a segment stack, I should say, using the PSEP protocol, right? So that's a PCE initiated policy, meaning you're not configuring anything. You're just configuring the PCE either through CLI on the PCE or through API interface. And this is also very important because then this is also leading us to some tools that we can use for getting SDN-like concepts, where you can program your paths to get some of the SDN concepts, which is by software we are creating paths on your network, right? You don't do that all the time. You do it where you want automation to create paths on the fly. It is not created a priori because of your service, but it's done in what we call as tactical needs. If something goes wrong, you want automation to go create something. That's where you'd use PC initiated. For most cases, you would do PCC, meaning the head end itself is configured with a tunnel, and the benefit of that is then you can bind it to a VPN service, right? It's a lot easier to bind a client, configured tunnel to a VPN service. When you configure the PCC initiated, we can configure the full policy. When we say a full policy, we are talking about a policy to this tail end with this color. So that's a static policy. And for every such tunnel or policy, you have configuration. The other one is on-demand next hop template. I just mentioned in the previous slide. So this is basically where you say, for this color, this is the treatment. And you can create this tunnel to any tail end on demand, meaning if a tail end advertises a prefix with that BGP color community, you know that that tail end is asking for a tunnel to be built to it. And at that point, you configure it. So your configurations go down to very small. You don't have to create a configuration per tail end policies, but you just create one template, and then on demand, those policies get created whenever the BGP signaling happens for that prefix with the color. So that's the two options there. Again, all of this I'm kind of recapping because we are going to see that in the in our how do we do it with Crosswork network controller. So let's recap quickly what are the use cases. These are very high level, let's say canonical even. This is why you typically do traffic engineering, whether it's RSCP or segment routing. Again, there are challenges in doing a lot of this with RSCPDE. You do it in a very minimalistic, where it is essential because you have a premium service or the specific need. But in segment routing, it becomes a lot easier to adopt, right? There are 5 categories, and we'll quickly look through those in detail here, right? So the first one is that you don't want to use the IGP cost for forwarding, right? Usually from point A to Z in your network, you let ISIS or OSPF figure out all the IGP costs and pick the lowest cost to send your traffic. But what if you don't want to send some traffic through that path, right? Normally, ISIS OSPF applies on all traffic going through all network from all points in your network, right? There is no choice to actually move only a section of traffic to a different path. Let's say you have a traffic that has to go on the lowest latency path. For most other traffic, you would use the cheapest possible link. How do you do those kind of things, right? So then you need traffic engineering where, for example, in this example, we have the top path as the cheapest path from IGP cost. Usually it is also cheapest from the money perspective. But you want to send some premium traffic on the lowest latency links. Maybe those are the high cost links. Then you would create a longer path, and you could use traffic engineering to do that. And then you would do steering, meaning those traffic that needs to go through this green path, you would have to create some steering configuration to push it through that, right? So that's called traffic steering. Then you have affinity, and this turns out to be the most predominant use case for traffic engineering, which is you want certain traffic to follow only certain sub-topologies in your network. You have a large network, from point A to Z, all traffic will always follow the OSPF or ISIS paths, but what if there is a traffic that needs to follow only certain links? It cannot go on certain other links, and within the context of those sub-topologies, you still want to do shortest path, right? How do you do that? And one typical example is that if there is a customer that needs to use only certain links because of security reasons, right? Secure links, typically, government, defense or whatever may need that. There may be reason to avoid satellite links for some communication. There may be reason to, if you're a provider that is participating in different countries, you may say some traffic should be not use any link that crosses the international border. So in traffic engineering, both RSVP and segment routing, there is a way to actually put properties. Those properties are defined by yourself using what is called as link attributes, and used to be 32 bits. Each link can have up to 32 bits. Each of the bit is a property, and then when you create a path, create a tunnel or a policy, you can say, prefer only these links or restrict only the topology in which you're doing SPF to those links, right? So that's called traffic engineering affinity-based constraint, and this is one of the most predominant use cases, in which case, you may actually want to go only through those red links, which are marked as secure. You cannot use the other links. That's a very common use case. The other use case that is common is when you have a customer or a service that needs highly available traffic. They cannot take too much of outage, and you actually end up sending 2 copies of traffic. To make real sense, this traffic has to avoid sharing any link or node, because otherwise it's there's no point in sending 2 copies if a link outage or a node outage or any thing in the network causes both copies to be affected, right? So we see this typically in content delivery networks, multicast. There are devices that can actually listen to 2, S, Gs and then merge them. If a packet is lost on one, it'll pick up from the other. There are actually devices that can do that, and those customers need this. But the challenge as a network engineer is to figure out how can I ensure that the traffic actually does not go on the same link or node. Basically, it's called disjoint paths. Basically, you'd want the set of links and nodes for path A to be totally different from B. You can, of course, nail it up, right? You can configure these hops for this and this hop for this. But it's in a large network, it's a lot of overhead in terms of configuring and managing and keeping it up to date. You really want to tell the network that I want these 2 paths to be totally disjoint, and you figure out which are the best possible paths. After you figure it out, optimize it on the usual HB cost, latency, extra, right? So that's what is called as disjoint. One of the things at disjoint is that there is not only node link, you can do just links, you can do node and link, you can also do something called shared risk link groups. These are basically, you have to actually go configure your network. Again, in traffic engineering, there are possibilities of indicating that a link or a node belongs to a particular risk group. They share the same risk, right? So this is typical where you have, let's say, 2 links that is basically 2 different fibers, but they're going in the same conduit, right? If the conduit gets broken or has a fire or something, both links are going to go down, right? So you can actually indicate on those links which are the risk groups, and then you can request the routing function or the path calculation function to avoid also being on the same shared risk link group. Yes, it does need some overhead for shared risk link group, but most customers that need this kind of service will do it, right? They will need to go ahead and do it. And then bandwidth as a constraint, right? So now we are getting into a little bit more advanced topics. These are not easy things to do. In RSVP, there was a mechanism to actually track all the bandwidth requests in the RSVP protocol, and you would give basically a pool of bandwidth, reservable bandwidth configuration on every router and every link. And then when the RSVP request goes, it basically gets the bandwidth allocated for each request. And when a new one comes in and there's no bandwidth, it'll basically fail. That is called admission control kind of things. When you go into segment routing and SDN concept, we don't want that information to be spread out on the network. We actually want the centralized path compute element to manage it, and then basically keep track of how much bandwidth has been allocated to each service, and then figure out that there are paths where you can still reach from A to Z, but not the shortest path, but you go on a path where there's bandwidth available, and then you actually, create the service on the fly through those paths, right? And after you create those paths, you have to still keep monitoring bandwidth demands and see that, let's say the 1 to 2 path is suddenly idle and not more bandwidth capacity available. You want to re-optimize and make the green tunnel instead of going 142 to go back to 12, right? So those kind of options are available, but you need the path compute element to monitor your bandwidth utilization and keep track of bandwidth requests and all that. So that's another pretty common use case, and there's a lot of activity happening on that because there are more. There's a whole range of requests here. Some of them are what we call a soft bandwidth request, meaning protect my bandwidth for these services as much as you can, but it's not it's okay to move deconverge if needed. And there are also sometimes TDM-like services where you have to give a very hard bandwidth guarantee. Nothing, even if there's no traffic for that service, that bandwidth cannot be used, right? There's no chance of statistical multiplexing in that case. It is a little bit expensive service, but there are needs for that as well. And on that note, on segment routing, there is a new technology called circuit-style SR, segment route T, coming, which will really give you really hard bandwidth guarantees with the path protection. You'll have a main path and the protect path and a backup path. And the other interesting use case related to bandwidth scenario is bandwidth congestion, right? So bandwidth congestion is a little bit opposite of what bandwidth on demand did. In this case, what we're saying is that let all traffic go as normal, but then if there is a point where there is congestion, and that these are basically short-term congestions. When you have short-term congestion, it's not possible to go and run a fiber really quick. You have to do some mitigation in the duration of congestion. You need to react quickly and put some, let's say, bypass paths for the traffic that is causing congestion, and then maybe take it off when the congestion goes away, and tell your network expansion, capacity planning, procurement people to go plan to build out more capacity in that path if this keeps happening, right? So this is more tactical, congestion mitigation, and this is where traffic engineering helps. What you can do is if your one path, it's 2 to 3 is 70% congested, and that hits your threshold of what you consider congested, and you need to wean off some traffic off of that link, you can actually go ahead and create a traffic engineering policy to a path that is a little bit roundabout, but still has bandwidth capacity, and you can actually take a portion of traffic out and mitigate the congestion in 2 and 3. Typically, you do it for your low priority traffic, mostly internet traffic or best effort, so that your premium traffic is already going to 2 and 3, right, the shortest path. There's maybe some decisions made to send the traffic that way. You don't want to move that, but you can take some low priority traffic and move it away, and that way you at least get some breathing room to go ahead and figure out why there is, is it just a time-based congestion, or is there a long-term trend that you need to actually add, more ports and feeds and things like that, right? So this is an interesting area as well. With SDN and automation, this becomes feasible because you can actually have the network SDN controller watch your links, and you can set some policies up saying that if it's crossing a congestion link, not only go create the bypass path, but also auto-steer some traffic, right? So a lot of these tool sets and technologies, well, the main technology that's enabling all of this is segment routing traffic engineering, right? And then the tool set that we're talking about is the SDN controller that can do all these things on the fly. And we'll look at some of the examples of that. So we mentioned SDN many times already, software-defined networking, right? The software-defined networking concept has been around, I don't know, maybe 8, 10 years or even more at this point. The intent is that your routers are, very simplistic. You don't need to configure them for delivering a service. You have this SDN controller, a intelligent thing that goes and tells your routers to pin a data plane path. That's how it started, right? But over a period of time, we have come to realize that it is not very rigid. You don't have to break your control plane, data plane, right? The original view it was that the routers are just pure data planes, and then all the control plane intelligence in the router, in the controller. Controller figures out, all your forwarding tables, and just programs your hardware, right? And there are implementations like that with OpenFlow, for example. But if you step back and look at a more generic, principle here, what we are saying is that we want, through software, pick our paths, not only our like VPN services, but also the underlay paths, or the paths through which the packets actually flow through your network. And this is where segment routing is really helpful, right? To recap, right, segment routing is a source route paradigm, meaning the router is not getting every packet, looking at its routing table, and figuring out next hop. We are actually telling the starting point, which is the head-end router in the segment routing network, to actually put the source routed path in the segment list and put it in the packet and send it, right? Every intermediate node can look at the segment list and then figure out where it has to send it, right? Typically, in a single IGP area, because of the way MPLS works, we just put the node segment ID, node SID or prefix SID as we call it, and the MPLS label swap works fine, and you don't need to do more, right? So the point being that when you use source routing paradigm, you have a lot more control over which path your traffic and your services take, and then you can actually go and configure those paths per service on your head ends, right? But you don't want to configure it, because that'll defeat the whole purpose of getting the benefit of SDN. To get SDN, you would need a centralized path control, which is basically your SDN controller, which will basically take your intent as it is and take your constraints, and then it calculates and sends a path to the head end to use those, right? So that's why segment routing is very SDN-oriented, or enabler of SDN, if you will. And the final thing is that you don't want to keep configuring it through even your SDN controller doesn't want to use your traditional human interfaces. You want some programmable interfaces here, and this is where your netconf and your PSAP protocol and even the operational stuff through telemetry is super helpful, because machine to machine, right? Routers are machines, the controls are machine. You want a better, more efficient mechanism to actually program your network rather than using CLI and looking at prompt and things like that. That used to be in the legacy or previous implementations. So basically, with segment routing and all the programmability approaches, we are able to actually adopt SDN with segment routing quite easily. Now stepping back further, let's say you're a network operator, network engineer. You don't care about the underlying technology, but you have to deliver services, right? So what do you want your SDN controller to do, right? So you want it to be able to turn up services quickly, whatever the service might be. Typically, in the transport world, we are talking about L2 VPNs, L3 VPNs of different flavors and technologies. So you want automated provisioning of that. You want also to be able to see those VPNs deployed, meaning you want the controller to be like a mirror image of your network. You don't want to log into routers every time you want to check something. You want to be able to go to a UI user interface and see your VPNs are deployed, which sites, what are the key parameters, right? For humans to be very efficient, images work very well, right? Network engineers can see topology and immediately understand what it is. They can also, if you're a CCIE, become very good at CLI, but it's still, an order of magnitude more work of labor to go and do show commands on routers. You want that information to be, as we say, on the fingertips, right? And then these services, once they're deployed, you want service health monitoring to start as well. In the past, what would be is multiple OSS stacks and some operational tools, totally independent, but we want all of them together, meaning if we created a service, we want them, the health also to be told to us by the same platform, if you will, right? And then the bottom few things are related to segment routing or traffic engineering in general, but we want to also tie these VPNs to specific SLAs beyond what our routing can give us. This is where the traffic engineering piece comes in. We want those SLAs to be honored even when the links and nodes are flapping or changing. Topologies change all the time, but if I asked you to go through affinity to a set of secure links or whatever, if those links flapped, I want the network to automatically switch to a different path. I don't need to, nail up these things that won't be practically useful. And then bandwidth use cases are a big one. And bandwidth use cases are an example of a little bit sophisticated thing you can do when you have this kind of automation, where you can add more and more apps that can do more useful things automatically. But there are a lot more things you want to do, right, through automation. So if you want to step back and look, what do you want to do in terms of the overall network management piece, then you would start from day zero, right? Where you're getting a router ordered, the router actually shows up at a site. Somebody goes physically installs, turns it up, connects. You want that job to be as easy as possible. You don't want too much time to be spent on site. Particularly if you're deploying a large network with the 5G deployment, you're upgrading all your cell site routers. This can be a lot of work. So we do need automation there. We call that ZTP, zero touch provisioning. There's even a standard for that. Basically, the router, when it's powered on the first time, it calls home and gets all its configuration, right? Once it's up and running, before you actually put it into service, you do some compliance checks, pre-checks, make sure your images and patches are on up to date, all of that, integrated with tools that you have. That's what we call as day one. And day two, it's ready for service, which is where you're provisioning your VPNs and traffic engineering. At that point, you want monitoring of the services, your network monitoring. But there are also other things. You may want to do, planned maintenance, right? You may want to update your, patches, smooths on the XR. And then you want to do auto remediation when some faults occur, right? Usually, if it's a link failure, no problem. The routing takes care of it. What if it's a brownout? If the fiber is not failing in a graceful way, but you're getting more and more CRC errors, indicating that something is going wrong. Either the optic is failing or your fiber is, slowly degrading and breaking apart. You'd rather detect this kind of failure by monitoring a KPI like packet loss rate, for example, or CRC errors, and then shut the link down yourself, and then have somebody go and fix it, right? So that's called auto remediation. There are some tools that you need for that. And then, of course, longer term, you want to get some data about how your traffic trends are behaving. You want that to be come from the same source rather than build another tool for it, right? Again, this is going into a little bit deeper into your service ordering. Actually, I'll go use this picture to talk about it. Usually, for the day two, when we talk about service turn-up, usually there's a business order system, which is the front end when your customer calls in and they require a particular service, a VPN service, which are the locations they need it, right? Which are the, connection points, and what is the kind of service, L3, L2, etc. All of that goes into usually some kind of ticketing system. There is some human involved in deciding and agreeing with the customer that they will connect to here the PEC subnets, if you will, or you may have some policy. You will tell the customer what they have to set up on their side. Usually there's a workflow automation tool here where for every stage, there is somebody who is authorized to decide these things or negotiate these things with the end customer and fill the information. And it goes through policy where, at some point you'll come to the your own policy, which is you're a provider, you have to pick the route distinguisher, for example, or route target. That's totally your policy. You may have tools and inventory systems, IPAM, IP address management, all of that. And it basically is an iterative process, right? At some point, somebody looks at everything is filled up, now go provision it, right? This is where the automation kicks in. You have enough information that you can actually go configure the routers. And then when you configure the routers, if you have to do segment routing TE or even traditional RCP, you use a different tool to get the paths, and then you can go to the health monitoring systems, you re-enter. What I'm trying to show you here is that in the legacy way, there are just too many tools here, and all of those have to work in concert with different teams of operational teams and turn-up teams and activation teams, right? But what we are saying now is that we can actually merge a lot of these into one platform, what we are calling as SDN controller, wherein you have one interface, API interface, to actually take the order, and it actually does all of it inside to, let's say, east-west communications, all encapsulated into this controller, and then the only thing you get out of it is notifications about either service completions or alarms and service health issues, so that you actually are getting the benefit of all the things inside can be aware of each other rather than having to go outside and do each in a silo, right? So we're trying to break silos here to make sure they all work together, right? But this SDN controller can be a big thing in itself, right? We don't want something to be so big that it cannot be, it basically comes to a point where it can't be changed anymore because it's just too complex. There's a full matrix of connection and dependencies. So we don't want this to be too big to fail or too hard to change kind of a model, right? So there's a lot of discussion in the industry about this. So there is a RFC 8443, which is laying out some architectural overview of how to manage large multi-domain, multi-layer networks through automation. The vision there is that there is actually a hierarchy of controllers. Each controller is specialist in its domain. For example, for IP domain, there would be an IP controller, right? What I'm calling a transport controller on IP networks. And there could be one for optical domain. And if you are, a lot of our large customers actually have multi-vendor policy. They may say region A is vendor A, region B is vendor B. In that case, you may have a controller for region A and different controller for B. And then what you would do is you would put them together so that there is one let's say, a single pane of glass or something like that, what we are calling now as hierarchical controller, right? A hierarchical controller basically has API integration with the, downward domain-specific controllers. These domain-specific controllers are built by the experts in that domain, right? If it's optical domain, they're optical experts. It's IP domain, then, segment routing, TE, and all that, then those people would build it. And then you may actually want to put them together to get a global view, right? Your services may span multiple domains. Typically, optical and IP are always together, so you may want to have optical IP, and in some cases, microwave. The hierarchical controller can merge all of them and show them in one view, right? And if you have noticed, Cisco acquired a company called Sedona, NetFusion. They're a very popular hierarchical controller that can actually work with many vendor optical systems, and they can also integrate with IP systems. And we encountered them in many customers, and they have a very strong product. So now they are part of Cisco now, and we are calling them the Crosswalk Hierarchical Controller. And the main job there is to actually, via API, integrate with these subsidiary controllers and to integrate and present the information back, right? It's actually interesting that that layer is actually not very complex or big because it's all about API integration and presentation, right? It's mainly to enable you to see a global view of all your services together, but all of the intelligence are actually to translate it into real technology-related specific configurations is done by the next layer below, right? The other example is when we look into 5G, right? 5G transport slicing, as some of you might know, it has really three components. You have the radio access network, and then you have the packet core, and in the middle, you have an MPLS network where you have to actually create the transport services, L3 VPNs, L2 VPNs, and things like that. So you end up with three controllers. Each of them are domain specialists, right? The IP controller does all the segment routing, TE, and VPNs, and the other two controllers do their packet core domain-specific and RAN-specific things. But then you want a global view of your service, you can actually have a hierarchical controller do that. The other use case is federation. If you have really large domains and you don't want one single controller to become too important, right? You have a single failure, your whole network may be affected. You may do a theater-specific controller, and you may want to federate them using a hierarchical controller. Now, when you have all these layers, then the integration could become a challenge, right? So there is a lot of thought being given to that. And the industry trend is to actually go into standardizing these interfaces, right? In this case, for example, there's a bunch of RFCs being written to standardize the models in which you actually create these services down below. That is pretty much almost like an RFC draft track for every type of service you can think of, right? L3 VPN network model actually specifies for creating an L3 VPN, what are the things that you would need to actually create them on the network. So there's a standard YANG model. There's a lot of discussion about adapting that. And then basically your controller would provide that as the API interface, right? You would, your north end, anything that is north of it, a business system or a workflow engine can actually use that model to create L3 VPNs using the standard model. That way, the developers of those software components which are outside of the controller, they have a very standardized interface, right? YANG models are the common language, let's say, to describe models. And then, so there are different YANG models that are in the north of controller, the way you access controller, right? That's there. There is also a vision to even have a customer-facing model where your customers can, on demand, go to your company's website and book their VPN, for example, and that is the highest level customer-to-service orchestration. Again, this is documented in the RFC that I mentioned here, 9182. There's a lot of debate, and as operators, you guys probably have a lot of strong opinions. You should look at this and continue the discussion there, and we can all make it better. So that's the top layers. This is the outward view of the controller, how you actually access the capability. Because the idea is that your whole network becomes one API endpoint, right? You're not touching each router one at a time, but you're actually asking the controller to go create a L3 VPN, and the language of asking that is the Yang model, right? Down south, from the controller to the routers, right, there is a lot of standardization happening there. The trend is to use netconf Yang to talk to the router devices, but the Yang models itself, the description of what every configuration possible on the router is, there are lots of Yang models that every vendor is producing. So Cisco has what we call as native Yang models. There is a lot of standardization happening there as well. There is a whole open config group that is creating a generic multi-vendor Yang model for, let's say, BGP. Every vendor supports BGP. BGP is a very well-known feature. Why do we need to have a Cisco model and a X vendor model and a Y vendor model? We would rather have one model that every vendor adopts, right? So that is also happening. You can actually find the GitHub links to go and look at those models. As with any standardization, right, by the time a standard gets written, the technology has some new innovation come up, and usually as vendors, we try to extend our models, and then it flows back into the standard-based models, and there is usually a lag. So if you're adopting latest technology, you have to be prepared that you'll see vendor-specific models that are coming out first, and then the open config models. The other thing is that it's just the story similar to your MIBs. I don't know how many of you touched SNMP MIBs, but there are standardized MIBs, but some of them are more standard than others. So the ones that get used more get fixed. When we say integer, we all mean the same thing, but some people may think integer means it's a string, right? That kind of thing happens a lot. But that at least there is a good starting point in terms of standardization. The idea is that when you get a controller that can talk to vendor A with a minimum effort, you should be able to talk to vendor B router, right? But that's let's say the aspiration, but there is always some test validation and fixing needed because of still some changes between the vendors. So now let's switch to the next topic, which is going to be Crosswalk Network Controller. So we built this product about, I want to say 3 years ago. We are actually up to 4.1. And it started by trying to address our segment routing TE, path calculation, and visualization as a problem. We started from there. And we always had this product called NSO, which is used for network orchestration to provision things. At some point, we said, actually, we can put both together and build all these applications on top, and it becomes like a controller because it can do quite a few things. So basically, we do support intent-based, what we call as intent-based automated provisioning, meaning you create L3 VPNs using our standard models, and we calculate the configurations for every device. We can do multi-vendor because we use NSO underneath. NSO is, if you're familiar with it, it was a company we acquired maybe 8 years ago. TailF was the original name. It is very powerful in translating configs from it's model-based, so you have the VPN model, and you have the device-specific models, and there is a translation layer, which it's been around. A lot of our customers use it. We have a lot of partners that can develop on it to extend and customize. The intent is that it's a development platform where you can actually extend easily, to your custom deployments. So we integrate with that, and then we have the whole segment routing path calculation piece. For that, we use XR 9000. Or any XR router that can do path calculation, we actually integrate with that, and we can create paths, and we can now integrate your VPN to those segment routing paths. With that, we get dynamic traffic engineering. We have bandwidth awareness in our controller. We have real-time network optimization. And we have a lot of day two assist, meaning once your services are provisioned, we don't want you to have to keep track of the configurations through different means or even log into routers. We want to show you as much as possible by point and click, right? That's the benefit of building tools that can visualize your network really quick. And then we build service health monitoring and network monitoring. So this is a very high-level view. The main application is built, the blue piece in this picture is basically a Kubernetes-based, microservice-based architecture where we have different apps that will light up the screen on different parts of the UI. And then the actual things that do the work, the path computation engine is a XR-based. There's a feature on iOS XR called Segment Routing Path Computation Engine. It has what we call as internal API. It's basically a REST API, but we use that to actually create paths or get notified of path requests, and then we actually provide you the UI to interface with it, right? The SRPC itself talks PSEP protocol and BGP link state with the network, right? This is important because we need to get the IGP information from all your IGP domains, and you would run one BGP link state to all your IGP instances so that all of the topology information can be taken into the PCE. PCE does path calculation also, but if it has a bandwidth-aware path calculation needs, it actually comes up to an app on the blue part of it, which is actually aware of bandwidth calculation. I'll explain that more later. To do path calculation in a bandwidth-aware case, we need to know how much bandwidth is currently being used. So for that, we need a way of collecting bandwidth consumption on every link of your network. We need a lot of telemetry, right? So the data collection layer is basically going to talk to all the routers. The simplest way or the most easiest and common way is to use SNMP, but we are also introducing GNMI-based interfaces to collect streaming telemetry. We can also do Cisco's model-driven telemetry, which is what we were supporting before GNMI came out. So this portion, for anybody that has worked in telemetry or data collection, there are a lot of open source tools out there, but it can be pretty intense in terms of the CPU, memory requirements. If you want to do massive scale telemetry, you need lots of resources, right? So the way we have built it separate out is that you can actually scale it. Each data gateway can handle X number of routers with so many KPIs it can collect. If you need to go more, you just add another VM and another VM. So we built it out separate so that we can scale that layer out. And then finally, NSO is our configuration engine. It keeps a config DB of the whole network. So every router's config is pulled into it. And then when you create a VPN, it can do calculation of what the router config changes should be, and it can actually send it to the router, right? So that's what NSO does. And it has all kinds of consistency checks. If you go ahead. The data gateway? Yeah, the question was, is the telemetry collector separate VM? Yes, in our implementation, the data gateway is one or more VMs. It's a scale-out architecture, so you install those VMs separately. By the way, the SRPC is also a separate VM. It can be a physical router, ASR9K 9900s, or it can be an XR9000. Because it's a pure control plane, we see most customers deploying it as XR9K. And NSO is definitely a VM as well. And you usually deploy 2 of those for HA reasons. The main blue portion is a Kubernetes cluster, so minimum of 3 nodes. And then as you scale up higher, you can add more worker nodes, right? So, but we have encapsulated all of it as easy to install, meaning you don't have to go to Kubernetes layer. We have an installer that you give it we support it on vCenter. We are going to support it on EC2, Amazon EC2, and we can support it on KVM as well, right? So you basically we have installer scripts that'll go fire up the VMs. You don't need to go into Kubernetes layer. We are kind of hiding it from you for now. But there are interesting requirements where our customers are asking, can you deploy your pods, as they call them in Kubernetes, on the customer's own Kubernetes or EKS. We are looking into those things as well. Let's now switch to a demo, and here's where I'll switch to a different screen and give you a flavor of how that works. All right. So this is a UI of Crosswalk Network Controller. And we have, this is the dashboard of the UI, right? Cross-Network Network Controller. As I said, we support different kinds of applications. Some of these are optional. You can do just traffic engineering and not get anything else if you want. Or you can do VPNs. You can do, at the bottom, I'll show you there are maintenance workflow engines. Let's actually, this is a recorded video. I do have live here as well if you want to see. But for now, let's play the video. So the traffic engineering, we support all flavors, including SRv6, which is new as of last release. And then we support multicast preset transport. We are one of the first controllers to support it. It's really new technology. And then we have VPN services, and we have a separate module to check the health. The maintenance playbooks, we call them. This is for maintenance operations. We have ZTP module. And then we actually, this is a view that shows you that we have it connected to a NSO as well as a PCE. So we basically have to add it. And then we have a bunch of data gateways, we call them. In this demo, I just have one. And all the devices are attached to data gateways. The data gateway or the collection layer is what is talking to device. Finally, you can go back and look at the, this is the software layer. Crosswalk cluster, like I said, is a blue piece in the diagram with the Kubernetes cluster. And then you have all of these apps that are installed on it, right? And this is a topology that we can visualize very easily. The SRPCE, which is deployed on the network, is running BGP link state with all your routing domains. We import the data, and then we can put it on a map. We do need you to enter the GPS coordinates. So we have APIs to do that, or you can export all the data and add latitude, longitude, and you can quickly see the visualization. These green links, by the way, they're green because that is those links are up and we're able to monitor them. As the traffic on those links start going up, we can color code them, right? If a link is like say, you can put thresholds. If it's more than 50, change it to yellow or something. We can do that.
How can they collect coordinates from SMP?
No, coordinates you hand enter, meaning through other.
Manually enter.
Yes, we have a. You can whatever we collect from PCE Auto Discover, we allow you to export into a spreadsheet, and then you can enter latitude, longitude, or you can use our API to update through script as well. Yeah, so that was just a quick intro. If no more questions, let's switch back to PowerPoint. So the next thing to look at is, in this system, how do you actually create segment routing TE, right? So for the demo purposes, what I narrowed down is that we'll create a policy that only uses certain links in the network, the same network that you saw in the topology. We will create a policy to go from one node to the other, but we want to do affinity, meaning not just the shortest path, but we want to pick, I have already laid out the link attributes, bit 10, to map to secure link, and then we want to create a policy that uses, secure links only, right? The way you create is you go to user interface and we have a form, you create the head end, tail end, color, and then you drill down to path option and you say constraint affinity. You can also do it through API. You can just push an API payload. We have examples in our demos with Postman or curl. But you can also take the same payload and push it to UI, and it just fills up the form magically. In a demo, that's a lot easier than I have to type. So I'm going to use that to show it. What I'm showing you is what is called as PCC, like client, Path Compute Client Configured Policy. There is also a way to do PCE in it. I'm not covering that, just to be clear. In that case, you would also go to UI, or you can use API to create it, but it actually does not configure the router. It uses PSEP to create a policy or a tunnel, and it's not in the config DB of the router. It's an operational data, meaning a policy came up. It's in the config DB of the PCE. So it's a little bit different than normal configuration. After the policy is created, the main thing is to be able to see it, right? I mean, you can always go to the router and do show command, which we will do, but we'll also see on the Crosswalk Network Controller how it appears. And then we'll go to a few more things. How does a disjoint path appear? How does an example of bandwidth on demand appear? I've already created those, so we can save time on seeing it. And let's switch to demo. So all of the action in terms of configuring happens under the segment routing traffic engineering. I hope it's not too small for the people in the back. And then you would go into provisioning. As you see, we call it provisioning NSO because we're basically sitting on top of NSO here. So what we're doing here now is to actually, I could have just clicked plus and it would open a form. I type in all the details. But what I'm going to do is I'm going to as you can see, you can download sample JSON and XML. This is the payload that you send through API. So I've created already the policy I want through JSON, and I'll just load it, and then we can view the form, how it looks. So now the UI is filled up with this data. You can see that we have, we are creating a policy, with a convention that SRT color 2004, going to tail end, that IP address. So the tail end loopback IP, or TEID as it's called, is what we have mentioned. The head end is going to be node 5, so we're going to 5 to 4. So that's what we're showing here. And then you come down, you see that the tail end IP and the color is mentioned. And then you pick the path, right? So you can actually, on ISXR, give a number of candidate paths, as we call them. It'll go in the lowest to highest order. And if the first one that is successful, it'll use that, right? So in this demo, we just have one. And here you see that you can actually choose either explicit path, in which you create a list of segments that you want this policy to go, or this candidate path to be. In this case, simple, right? We are going to use dynamic path. We are going to say IGP optimized, meaning minimize the metric, IGP metric. And then the PC checkbox, that's important. What we are saying, the head end is, head end, you don't do the calculation, you delegate the calculation to PC. So that checkbox to be checked is important. If you don't check that, the head end will do the calculation, which is fine if the tail end is in the same IGP, right? If it's in a different IGP, head end doesn't know how to do it. So you have to check that to let PC, the external component, do this. So now we go and look at constraints, and then you get the affinity. And here we say include a bunch of affinities. I'm including secure link. And here's the what we call as dry run. The main benefit of dry run is that we are looking at the change that will be pushed into the network before it's pushed, right? So it's basically telling NSO does the calculation. You have expressed an intent. Actually, if you scroll down further, you will see the what we call as the northbound model entries instance. Yeah, so we are creating the bottom part of it, which is device agnostic, right? If you have a different vendor device, it doesn't matter. You're creating a SR policy. This is a Yang model instance of that policy. And then the top part is the converted or calculated for iOS XR version of it, right? So you see both here, and then you decide whether you like it. This is the Yang model of the populated, and then the top one was the iOS XR model. So this is the iOS XR model. What we will see is that when we click submit, it's going to push that config to the router, the head-end router, which is, I think, node 5. And we can do if you are familiar with XR, you can do a show configuration, commit changes last one, and we'll see the exact change come in. So let's go ahead and do that. So this is the color. So let's go ahead and commit. So let me show you that the affinity is set. For example, here the secure link is set to bit position 10. As the policy comes up, you can go and check. So there is no policy before, and now we can check at the show config commit changes, and you see that it's there, right? So basically, this is how the XR config for a policy looks with the affinity constraint. You can do a show configuration, show segment routing, traffic engineering. You see a bunch of information here. So basically, it asked the PC for the path. The PC gave these segments, the dynamic PC valid. You see 3 segment identifiers. These are basically labels, but they're actually segment identifiers. Go to node 1, 7, and 4. This is what you would see in a show command level. But let's switch back to the controller and see that we can actually get a better view of this, right? So Yeah, so this is what we're going to focus here. And you can actually see the same thing on the controller. So here you see a list of all the SR policies. You click on the SR policy, you see the path overlaid on your topology. Then you go into view details, and you can see configuration. And you get all the details. You can actually click on the show IGP path to let the visualization calculate the IGP path between the segments. Because each segment is think of it as a loose hop. There are multiple other routing hops in between. You can see all of that. And then you can go in detail and see these are the segment identifiers. If you're familiar with segment routing, you know that there are segments that we are going through. And then, yep, so that was the view here. Now let's look at an instance of disjoint networks. So we are creating two disjoint paths, 251 and 20,051 and 20,052. They both are between the same two hidden tail and pairs, but they are going on two different paths. They are going on two different paths because we said in our intent to the controller that these two paths should be totally disjoint from each other. And how did we do that? You can actually see that we actually said association source, 0000. Basically, you have to put a number saying that any policy request that has the same number should be totally separated. And then the controller does figuring out all of that. Do you have a question? Sorry. Yeah, so the other one also has the same association source and group ID. Then the next one to look at is a bandwidth on demand policy. So let's look at 777. 777 is going this way, and then ECMP and to node 4. And then 778 is also between the same two node, but it uses totally different links. As you can see, it goes to like a Z-like thing, and the other one goes to other links. Now, why are they being separated, right? They're being separated because they're both bandwidth on demand policies, and they both are asking for a certain bandwidth. And the way we have set up this lab is that there's not enough bandwidth on the same links for both of them. So one of them is going through the IGP path, let's say, node to node SID of the node 4, and the 778 is actually going through. It has to do a little bit more calculation to avoid those links that the first policy used, and it is doing an adjacency SID to node 1, and then to node 7, and then to node 4, right? So this is where you get the power of it. You don't have to worry about which actual links they use. The system takes care of it for you. And then you can actually visualize very easily. When the system does a lot of things, it appears like magic. But as a network engineer, as an operator, you need to know what actually is happening, and you want to click and see this. And here you see the bandwidth optimization on demand, where we said use the path at maximum available bandwidth, right? So that's the thing. There is some other interesting thing. We actually keep a list of historical data. We can show you how much traffic is going through each policy, and we can also show any changes that happen to it at different timestamps. That gives you a historical view of traffic flowing through the policy as well as any changes that happened. Yes? Yes. So the question was, can we do different constraints together, bandwidth and other things? Today, it's not that you can take any two constraints and put them together. There are some restrictions, particularly when it comes to bandwidth, because when you add bandwidth, the policy calculation is done at a different app. On the PCE, you can do affinity with all of those metrics. Like IGP or latency and things like that. But when it comes to bandwidth, there are restrictions. I can probably get back to you with a table of what are the combinations we support. And finally, there is a TE dashboard. This is basically letting you to slice and dice all kinds of policies you have in your setup, and to look at to get a quick view of your top N policies and so on. Right. So let's keep going here. Okay, I have it here. So now let's look at creating VPN. In this case, I'm going to show you how to create an L3 VPN. And then we are going to use ODN templates. These are templates for bringing up segment routing policies whenever there's a prefix with a color. We are going to put templates for 4001.3, we'll do 4129 and 413 later. And then the PEC prefixes are going to be in 30-dot range. We are going to say that they should get the lowest latency path, which happens to be color 4003. So we create a route policy to put 4003, and then the ODN template's already there, and then we configure the VPN to use 4003, right? So let's go to the demo. And so we start again from segment routing and traffic engineering. In this case, we will go to look at, OK, VPN services. We are creating VPN 101. It doesn't exist now. So we are going to go to provisioning and then look at creating. First, we look at ODN templates. Let's look at ODN templates because I have already created those. There are, for every color, there's a template, and the colors, the templates look very similar to SR policy, except you don't have to give the tail end, right? That's the point of template, that it'll work with any tail end that needs it. And we put it in all the head ends where the VPN is going to have PE sites. It's going to be dynamic, and the only one constraint we have in it is basically that it's going to be optimized on latency. It's going to delegate to PC, right? So next thing we go and look at is a policy. We created a route policy. Again, this is how our config looks on the UI. We use two colors. Some prefixes are going to get IGP optimized, maybe data traffic, and maybe the customer has VoIP traffic that needs low latency. And we have mapped those prefixes to 4003, right? Sorry if it went too fast. And now we are loading the, we're actually creating the L3 VPN, right? Here's where we will slow down and look. So this, by the way, the reason why these names of VPN profile, all this is looking like this, is coming from the RFC for L3 NM. L3 network model, YANG model is being standardized. What we have done is we've taken that YANG model and used it as a northbound interface to us, right? So you can create, so that's why it's called a IE profile. IETF profile is what it is. And in this profile, you say which are the route targets this VPN uses, import, export. And then you can attach it to every PE, or you can do more fancy, that every PE does different route targets if you're doing hub and spoke or extra nets, for example. So you can see here that we are actually export policies, VPN 101 route policy that we created. That means every prefix that we get from customer, we run it to this L3 VPN policy as we convert it to a VPN v4 route, right? Export policy is applied to convert a customer route into a VPN v4 route. And then there is route targets also that's defined. If you go in here, you'll see that we are doing, these route targets, right? We are importing and exporting the same one, import, export both. I'll show you an example of iOS XR config. Then if you scroll down further, the VPN node section is where the PE sites are defined. And here you'll see the PEC link, as well as the route target, right? Again, all of this is coming from the IETF YANG model. Actually, the version we have now is a pre-RFC draft. The RFC has changed a few things, so in the next release, we'll adapt to that. So routing protocol is eBGP, as you can see here, and so on, right? So let's, it's BGP, the customer's prefix, customer's route, redistribute connected, all of that. And then you can do a dry run. In this case, you can see that here are the, configurations on each router. This is the iOS XR config, by the way. So here we are creating a VRF. We are putting an export policy, BGP session to the neighbor, and we do that for every PE, right? The plus means we are adding this config to the device, right? So we have an easy way to understand that. And then if you scroll down further, we would see it for, here's the actual IETF YANG model filled in, right? So it's called L3 VPN-network model. And the bottom part is the device agnostic model. This is what you sent from your API through API. And then we calculated the XR config. If you have a XC, that will be a different one. Was that a question? OK, so let's keep going here. Yeah, so the VPN nodes, these are the PEs. OK. Let me jump ahead a little bit. So yeah, once you submit it, it's in progress. If you go to the router and look, the configuration comes in just like you expected. You can see the route policy there. Let me, yeah. So we created the VRF, export policy, the eBGP session, the route distinguisher. We can take a look at the route policy itself. Okay, here's the ODN template that was created before. Here's the route policy that we created now. And this you will see the customer prefix here, right? So these prefixes, when you get from from the CE, you're going to add the color community and send it. And now if you look at the policy color 4003, because of on-demand next hop, because the router came up, it basically brought up, right? The lowest, that's a default candidate patch is always there. The lowest one is 100, and that's the one that came up, right? So it basically took 3 hops. And now we go to VPN view. So we can see that VPN 101 has been created. When you click on it, you see all the P sites that participate in the VPN, right? So basically 3. You can see the logical CE connection, meaning we are not managing the CE. Yeah, go ahead.
Can it support multi-vendor for service provisioning?
Yes, we can. There is a little bit of work to adapt to that vendor's config. It's not out of the box, meaning you have to change the model to southbound model entry, but you can do it. It uses NSO to configure the device, so if you know how to use NSO, it's the same thing. So here's the JSON payload that I actually loaded. If you notice, I loaded a JSON payload in the UI. You get it right here. So if you have a working example, you take it, you edit it, and you use it. Then you have links to all the policy. You can look here directly. Here's an interesting one, right? So we created, we are in the context of looking at VPN. You can click on transport. We have 3 PEs. So we set up a full mesh of tunnels automatically using ODN template. And you can see that all those 6 tunnels are showing up here. And you can actually see that the actual tunnel path. So for this VPN 101, traffic from 5 to 4 will go to this path. And this is very powerful because it's hard to do this kind of integration between VPN and SRT at the same time. Yeah, we use the PEC links. So in the demo, we don't have any real CE even. Yeah, you can, yeah. Yes. Yeah. It's basically like a prefix list type of thing. You can update it, or you can even make it like any route from that VPN customer color this way, right? If you just want to treat your customer route, like a route A should be treated one color, route B, then you need to know those routes a priori, right, beforehand. If you want to treat all the routes from the customer to some color, that's a lot easier. You don't need to know the route. Like, the way I did it, I actually had this prefix, this color kind of thing. Yeah. All right. So that was VPN provisioning. I think there's a little bit more to see here. I mean, basically, you can go and look at the segment routing details in the context of the VPN. So that's the thing. Let's move on to the next part of the demo. Yep. So again, just to recap, what happened was that we created a service. It went to the NSO. NSO has a VPN model API interface. It does a transformation. It pushes the config to the device. And then here's where you can see, every device type has a model. XR and XC, we support out of the It's well documented. There are a lot of developers, a lot of Cisco partners do it. The adaptation of the templates and the Python code. And then there's plugin to start monitoring. That's what that arrow is. We support talking to all these devices southbound. I mean, this is just the device that we talk to, the transport layer and the models. So we call them NEDs, so we have a lot of them. In terms of integrating with other vendors, we have done quite a few presentations already. If you want to extend the model itself, for example, the ITF model doesn't have a knob because L3VPN has been around. There's so many features and knobs. You can extend it. You can integrate it with with different vendor. If you have an NS already deployed with VPNs, you can adapt it with CNC and so on. Everything would need a little bit of test validation. So here's a quick update on how the segment routing portion of the functionality works. Basically, it interacts with the network using IGP and BGPLS. And on top of the iOS XR piece, we have an app running on the top, which is actually collecting SNMP telemetry, and that's the bandwidth-aware piece, right? So that's the piece that's doing the path calculation. I'm actually going to skip this demo. I want to explain this congestion mitigation as well. So we do support a form of congestion mitigation in CNC, and this is basically what we call as tactical traffic engineering. So basically, when you send when we detect congestion on this link 2 to 3, we can actually compare it against a threshold. And once we detect the congestion hitting a threshold, we can actually go ahead and figure out how much traffic can be moved off the link, right? And then we actually do this, what we call as a path computation to figure out which path has bandwidth available to move this traffic. And then we create paths. We actually create multiple paths, and then we expect the router 2, node 2, to actually do ECMP between them, right? So that feature is called ECMP with one-hop tunnels. On iOS XR, it's supported in ASR 9000 in 731. In NCS platform, it's supported in 732. So there is a dependency that the feature, the router itself supports the feature. All we are doing is we are creating those tunnels on the fly when we detect congestion. So when the tunnel is built up, then we actually monitor the life cycle of the tunnel. So here's a quick view of setting the bandwidth occupancy between different links. So in this case, anything less than 5 is green, anything less than 18% is yellow. And why is this important? Because in the next demo I'm going to show you, we are going to use those values. So this is a demo of the link congestion. So here, I'm sending some traffic. It's going from 5 to 4, through 5 to 8 and 3 to 4. Those are actually running hot. And why are they running hot? You can click on those to see. If you go to link, we support both IPv4 v6, so you're seeing both. So you see it's about 20%. And why is 20% coming up as red? Because if you remember the previous picture, I set the threshold to 18 and above as that. So if you go to congestion module, you'll see that it is already complaining about congestion. And why is it saying it's congested? Because I set the threshold, I enabled it, and I set it to 18. Anything above 18, I want it to be considered as congested. Now, what can we do about it? You can go to operational dashboard and see that it has detected those two links. The threshold is 18, but we are actually measuring higher traffic, right, 20%. I'm basically sending a 2 MB per second stream, and I've set the reference bandwidth to 10 megabits per second. Now, what can you do about it? We are proposing a solution, which is create a set of policies, and you can preview those, right? Meaning, we have not created it yet. We're going to let you look at it, and all we are doing is creating 2 ECMP tunnels on node 5, and also we are creating 2 ECMP tunnels on node 3. The expectation is that it'll move half the traffic away, right, because when you do ECMP, and that'll bring it down. That's enough to bring it down below the 18% threshold. If you like the solution, you can actually go and commit it. This will basically go using PSEP. The controller is going to create those policies, right? This is not going to configure via CLI, because for this kind of tunnels, it's better to use PSEP. This programming the network. It's going to mitigating because it's now policies have been deployed. Let's wait and see if it actually saves the thing. If it saves it, we'll change it to mitigated, meaning if it removes congestion. Here, the actual policy has been created. It's not a preview now. And you can actually see the details of it here. You can get rid of the path that was congested and look at the roundabout path. What you will see, interestingly enough, is that it is an explicitly calculated path. It's a type LCM, right? We created the policy from the controller. And then it is, let's expand it further, and I'll move this thing off here. You'll see that it has explicit paths with those 2 hops, right? So that's a key thing to note. Path type explicit, and then adjacency set to the bypass node, and then from bypass node comes back through node SID, which is basically least cost path at that point. So that's interesting that you can see all of that without logging to router, right? And this all happened just by one click that you're able to relieve congestion. Usually the congestion mitigation takes that mitigated takes some time because we don't poll the router like too often to prevent it from getting hit, right, with SMP load. So we do it every 5 minutes. So this update, I cut down the video, but it takes 5 minutes to update. Now that we are measuring to SNMP traffic has shifted, we can tell you that it's mitigated. We are measuring now 12%, and it is because we created those bypass tunnels, so it's mitigated, and you can lifecycle manage those policies from there. 18% threshold, we are below that, so we are good. I think there's a view of the topology now, which you can just see that because we do color coding based on the traffic occupancy, it has gone down to yellow.
These bandwidths collected via telemetry?
We are currently collecting via SNMP because we found that's the best way to do multi-vendor. We are trying to shift to GNMI-based telemetry collection as well. Yeah, so that's that. I'm actually at the very end. There is one more topic I hope to cover, but I'm running late on time. I'll just introduce the topic, but I won't do the demo for it. I hope so service health is a very important topic. This is the latest release has the support. What we are doing is that there is actually an architectural draft in IETF called SANE, right? Service Assurance for Internet Networks. And the concept is simple, right? Many people have actually developed assurance stacks for services where we can look at the configuration of routers and then we develop some kind of assurance thing. But what we are saying is that we can automate the process of this whole thing by actually looking at config.db, doing some programmatic calculation of what KPI tells me the health of the service, and automatically turn on the telemetry for that, collect that, and present it in the context of service health, right? So the way our system works is that as soon as you create a service and you enable service monitoring, it sends a notification to there is a separate app you have to install, in the blue piece. It actually looks at what we call a heuristics package for the rules. For L3 VPN, for example, check the PEC link, check the PEC BGP session, check the VPN v4 BGP session, check that you have at least one route from all the remote PEs. These are the kinds of things you can do. You can express it in heuristic package. And all the data to do let's say, the show commands you would do as an engineer is already there in the config.db, right? So we automate let's say, the status collection information, and we actually get it through telemetry, SNMP, some of it through CLI, because it actually works best with that. And then we start collecting, we tell the data gateway, which is our collection layer, to go ahead and start collecting it. As the telemetry comes in, we calculate that, and we show it as a result here, right? So unfortunately, I'm out of time to show that demo. We support pre-SID, we support SRv6, we can do path trace, which is from any P to any P, show me all the paths that are possible, right? In this case, we are doing trace route SRMPLS, and then showing on the screen all the paths that can be used. This is important for places where you're not even using SRTE. You need to know just the path from A to B, which are the segment routing paths available, right? So that's another feature that's coming. Well, it's already there, I mean to say. So that's a good one. We support Flex Algo, so we can actually visualize Flex Algo on the screen. SRIGP Flex Algo is a very powerful tool to simplify and break down your network into sub-topologies. You don't have to do traffic engineering if you only want a low latency topology and maybe two topologies with affinity. With Flex Algo, you can actually use the same ISS to divide your network into, use different metrics or create a topology with affinity and those things. So with that, I'll stop and see if there are any questions. Please do the survey. It'll be helpful for us to make the content more appropriate for you. And then, yeah, please continue. This session will be, I believe, recorded and on demand. Please share it with your colleagues. Please reach out to me on WebEx Teams room or any other way you need to. And I'm here to answer any questions. I didn't want to go over time, so I'm going to stop here. If anybody wants to see the demo we skipped, I can show it to you. We can go to the Meet the Engineer or here. I'm here till the end of day tomorrow. Please feel free to reach and ask me any questions. And again, I'll wait here if you want to ask any questions. Thank you so much.